Good morning and welcome to Monday of week 5 of your Physics 5 a day. And we're starting today with the strong force. And we're going to see, first of all, why it needs to be so strong. Why did it get given this name? And to do that, we're going to consider two protons inside the nucleus. And there they will be about 1 femtometre apart. So that's 1 times 10 to the minus 15 metres. That's how far apart they are. Okay, so pulling in formulae from across the rest of your A-level, we can calculate the gravitational force they exert on each other. And that comes out as a paltry 1.86 times 10 to the minus 34 newtons, absolutely tiny. And remember that minus sign there means attraction. So this is the attractive force that each one exerts on the other one. But we know that they are both positively charged, and so they're also going to be exerting electric forces on each other, and those will be repulsive. So if we put all the numbers into that formula, we get a whopping 230 newtons. So this is the force that they're pushing apart with, and that's the force that they're pulling together with. So I think you see the problem. There has to be another force there. There just has to be another force there. Otherwise, nuclei would just blow themselves apart. The protons in a nucleus would just blow it apart. And we know that doesn't happen. We know that there are nuclei. Nuclei exist. So this is why scientists postulated the existence of another force. And it's also why they called it the strong force. But it is unlike any force you have ever seen before because this is its graph. So first very strange thing, notice that sometimes it's repulsive and sometimes it's attractive, and when it changes depends on how close together the particles are. So if the particles are closer together than about 0.5 femtometers, the force is repulsive, and the closer together they get, the bigger and bigger that repulsive force becomes. However, if they are further apart than 0.5 femtometers, then they're going to attract each other, and the further apart they get there, the bigger and bigger the attractive force becomes. And so what you get is nucleons, so protons and neutrons, that are it's kind of like they've got like a little spring between them. And if they get a bit closer, then they push each other away again, and then they get a bit further apart and they pull each other together again, and they sort of like bounce backwards and forwards in there. And that's how the nucleus is kept together. Now notice that should the further and further apart, the bigger and bigger the attractive force is to try and pull it back together again, but then there is a peak, and so if they do somehow manage to get further apart than about 3 femtometers, then the strong force is basically negligible. They basically don't exert strong forces on each other anymore. And then, without that strong force present, the particle just shoots off, pushed away by the electrostatic repulsion. So there you have it, the strong force, a very unusual one. You do need to remember these numbers. You do need to remember that the closer together than 0.5 femtometers, it's repulsive. And then after 0.5 femtometers, it's attractive. And then after 3 femtometers, it's basically zero. Those are the things you need to remember.